Hello everyone and welcome to Mplant's Paper Club. Today I'm presenting second time in a row, and today we'll talk about how GNNs can be represented as gradient flows. It's one of those papers where we use knowledge about physics, about physical systems, to interpret and improve machine learning models. So this time, the paper is written by Michael Bronstein's group. They're all from Twitter, but he's also associated with Oxford University. Cool. So let's start with an introduction and a brief abstract. First, I want to say that the paper is quite mathematical. As you can see, 39 pages means there is a long appendix with all the proofs. But one of my favorite things here was that even mathematical proofs were written informally in the main paper, which means it's easier to understand. If you want to get to the details, you can go to the appendix and read the maths behind it, but the intuition is given in the main paper. And the focus is on the intuition, which is great. So the main idea here is that we can represent a deep learning model, in this case, GNNs, or more specifically, graph convolutional neural networks, as a gradient flow model, which is used very commonly in physics to study dynamical systems, how particles interact. And basically, the layers represent the discretized timestamps in a gradient flow model. Of course, we look at the details of gradient flows, definitions, and how they are used to represent GNNs. And this representation will also help us understand limitations of GNNs and also discover some not true limitations. For example, there are a few things that we have always assumed to be inherent limitations in GCNs, but turns out they can actually be mitigated. Okay, so any comments before I continue here? Cool. All right. Paper starts with a general motivation and contributions. As I said, the main motivation is that is in the spirit of neural ODEs. Okay, so this dynamical system is also actually an ODE because it can be discretized and solved as a differential equation. Here there is a nice drawing representing the idea of how gradient flows can show us the benefits of how the limitations of GCNs can be mitigated. So there are three main limitations that are covered here. So the first one is the over-smoothing, and the other one is squeezing. So over-smoothing means as we pass messages across nodes or layers, features on nodes become more similar to each other. Right. So if you have a very deep model, you might end up with node representations that are all very similar to each other. The other problem is that as we propagate, as we pass messages across multiple layers or multiple nodes in the graph, information is lost there. Okay. So here in this diagram, we are looking at a case where an example where gradient flow dynamics can separate similar nodes. This is a problem with with over squishing. So the problem arises from the assumption that neighboring nodes in the graph should have similar features or similar labels. We'll talk about these two cases later on. For GNN, specifically for GCN, to be effective. For example, if you look on the left side, so the red and blue nodes would represent similarities between those nodes. But they can actually be near each other, be neighbors, but not have the same features or similar features. Similar is a vague term, but you know what it means, right? Now, the point is that we can using the knowledge from physics, from dynamical systems studied in physics, we can actually devise methods that will be able to distinguish, will be able to separate nodes that have different features despite being neighbors, right? So as you can see here on the left side, reds and blues are kind of mixed, and on the right side, blues are together, reds are together, right? And this is important. This specific example is about labels, and this is an important property to be able to solve problems where we have heterophilic labels. Okay? So we will talk a lot about homophilic and heterophilic labels. The first one means labels are similar when across neighboring nodes. Heterophilic means they are different. Okay? And we will see that that we can devise methods that are able to separate different nodes, but also keep the similar ones close to each other. Okay. Any comments here?
I have a quick question. So by different features, do you mean, for example, one node would have temperature and another node would have humidity, for example?
No, I mean the values. So if you look at
as in the values are different, or the actual feature itself
is
different? Okay.
So this is actually about the labels. So let's just talk about the labels. So for example, you would assume that neighboring, if it's a classification, you would assume that the neighboring nodes have same classes, or most of the time same classes, right? So the classes change more gradually as you go further from the given node.
And mathematically, each node is the same, right? So like has the same number of dimensions, the same.
Yeah, of course.
Allowed. Okay, that's fine.
Yes, we always have the same dimensions on features on each node. Yes. Anything else? Okay. Now we are going to start by looking at the Dirichlet energy, which is the classical standard energy model. We look at the formula later, but it's a energy commonly studied in physics, and we will represent GNNs using the Dirichlet energy models, but we will also go beyond that to allow adding parameters, because if you only look at the standard Dirichlet energy model, we are only able to model non-parametric cases and only incorporate labels. And we will also need to add nonlinearities.
Well, I found quite interesting. I wouldn't take the energy analogy too far actually here, because typically in physical systems you have also momentum, right? That pushes stuff, and here it doesn't. There is no momentum, right? It only goes to wherever it feels the most comfortable. So yeah, just found a bit funny.
Yeah, that's a good point.
Yeah,
I didn't think of that. Yeah, that's actually Good point.
Well, I think it just goes down sort of the steepest descent down the energy.
Exactly. That's nothing physical. That's
yeah.
just like standard math, isn't it?
Yeah.
Yeah. That's a good point. Yes, they always take the steep descent direction, so negative gradient. Cool. So we are going to start with, well, notation. I guess most of it is standard. We have a graph. We have so the graph is weighted but undirected. Undirected is important because there is an interpretation when we switch to weight signs. I guess if it's directed, you would have to switch directions, but we assume undirected graphs here. We will look at the normalized adjusting metrics, also very common in GNNs. We will have a feature matrix. We will look at the eigenvalues quite a bit. So the plus would mean the largest positive eigenvalue, minus would mean the smallest or largest in terms of absolute value, negative eigenvalue. We will have some results that cover the spectral radius. The dot denotes the temporal derivative, so it's a dynamical system derivative over the time. There are canonical products used in some of the theorems, but I guess we don't need to look at it too much. And oh yeah, and then we will also talk about almost everywhere with regard to Lebesgue measure in some theorems. But again, I think that's okay unless we go into the math details. Okay.
One question: what was the spectral radius again?
It's the largest eigenvalue of the matrix.
Yeah, because I think it
Yeah.
comes from when you apply the system over and over again, that one sort of filters
Yeah.
itself out, right? Yeah. Thanks.
Yeah, because this disappears in some bounds later. But again, it's basically it will be a constant depending on the I think on the weight matrix, but we'll see the results later. Yeah. Okay. So we start with the non-parametric case. So non-parametric means we don't we write the models as Dirichlet energy. The formula is right here. This is definition for Dirichlet energy. So F is the feature matrix, and we can calculate the gradients element wise, sum the norm squares. This would define the Dirichlet energy. I guess normally you would see this as a integral here instead of a sum. But we have a we will only look at discretized systems. And they also show some results that this norm is actually can be written by the trace. Trace really is the norm. Trace is the sum of diagonal elements of a square matrix, also the sum of eigenvalues. And we can write this as also a vector product. But we are going to look at the Dirichlet energy here, and we talk about non-parametric case because here we will consider only label propagation, right? And this has been studied before. There have been papers that looked at label propagations as dynamical systems, and this is more of a previous work analysis, and then we will see how this is extended in the next section. It's important, yeah. Arvid?
Yeah, this is where maybe found the original picture a bit misleading, right? If you scroll up, if you think about the dynamics, it's actually not the nodes themselves that are moving, right? Because the adjacency matrix of the node itself does not change. It's actually the values on those nodes are the things that seem to be flowing. So I was struggling a bit with yeah.
Yes. Yeah, so that's a very fair point. Adjusted matrix does not change. I mean, it doesn't change here either, right? Because the edges are the same. What changes is that their distance. So we will find we end up with a new basis for the feature space where these nodes are closer to each other, and we are changing the basis.
Yeah,
that's the change, not the just symmetrics. Yes.
Yeah, so the dynamics would technically be in a space that is the space of those nodes.
Features, right? Not features.
No, yeah. So in this case, actually it makes sense. If you have two labels, it's a actually two label system would be one dimensional, right? Because either you have the standard label or not. So it would be a motion sort of in a one dimensional direction.
Yeah, it would be a two-dimensional system, and I guess
time in one direction, and then the node moves either closer to one label or
I think the weight matrix would just have like one and everything else zeros, like one in the top left or something like that. Yeah.
What do you mean the weight matrix?
Because later they introduce the weight matrix W for the forward integration of the dynamical system.
Yeah.
Oh, that weight matrix.
Yeah, and I think that's how they get this separation by evolving that system.
Yeah. So we can look here in the formula.
But I think the Dirichlet energy computation actually is really interesting. Like I hadn't seen it before as like a measure of smoothness, because it's what like the L2 norm of the difference in features between neighboring features. So if the features are sort of very different, so you'll have a huge Dirichlet energy, so it's not smooth at all. But yeah, I don't know. I thought the concept was pretty interesting because I hadn't seen it before. In discrete sense anyway.
Yep. Yep. So the goal is that we have some node features, initial node features, F0s, right? We have some labels in the training set. So for some nodes, we have labels, and we want to predict labels on some other nodes we test. Yeah. And the way we do it is, well, first we write the dynamical equation here. So the ODE. So we want to find the y's, so the second term here is the smoothing part, right? So we can actually write this as if you define the y, well, the gradient of y, but at y as the Dirichlet energy, we end up with this formula here, formula 3. So the left side is the smoothing bit, as Naif just said, and the Dirichlet energy plus the smoothing bit between layers. Okay. Now, the argument is that, well, this is fine, but there is nothing about the features, right? Not features. And to enable that, we are going to add to parameterize this equation to enable features, to study how features change. This is so far only about label propagation. Okay. And to do that, we will define it again, a discretized version of a dynamic system to study GNNs. So at time t, tau is the time interval for discretization. We would have the ft. So this is the residual term, right? As we will see later, this becomes quite important. Plus the tau times the GNN, parameterize this time with thetas. And the inputs for the GNN are the graph and the feature vectors at the current time t. Okay. Cool. And of course, this results in a feature evolution over time, and thetas are learned by backpropagation, and there is a loss for the specific task, whatever task we are trying to solve. Right? So we are actually quite abstract about the loss part here and the task in general. Okay, so let's scroll a bit slower. Now, next bit talks about energies, how we can define graph convolutional models using the energy, right? So how is that model generic enough to represent different channels? So here we introduce a generic class of graph convolutions in equation 5, which is a case for the equation 4, but with some more weights, and I will discuss what those are and how they cover different well-known GNNs. So the FT part is the same. Tau, the sigma is the nonlinearity, and here inside we have 3 terms, right? We have the omega, the minus f omega t, and then we have wt and w tilde t. Now the adjusting matrix appears. This is the normalized adjusting matrix. Appears only with the wt. So wt will be the mixing part, right? This is the diffusion part. This is the only place where features on neighboring nodes are diffused, are mixed. The other 2 don't have that part, and all 3 of those matrices are performing what's called channel mixing.
What is actually the difference between the first and the last part? The last part, it looks we have F0,
F0. Yeah, so this is the original one.
Essentially, we have a long-term memory in our system.
Is it memory though? This is only the original input, right? I would say long-term memory if you have like all previous steps. This is more like the input condition. I would see it that way. No?
But if you make tau to very small, right, then this term is still sizable compared to all the other ones, right? So
Tau small.
Yeah.
Yeah.
Yeah, so it is. Yeah, I guess it is sort of like memory term because you still retain some information from the initial condition.
Yeah.
But only the initial condition, right?
Yeah. But from what I remember,
where you put your 0 matters now, right? You change t into a different system, then your equation does change.
Yes.
I think this comes from the original neural ODE literature, where they had an initial condition. I don't remember how they actually wrote it down, but you do have some sort of influence. Yeah.
But if you take the derivative with respect to tau, right? So you can get a differential equation, and that differential equation itself depends on the initial F0. I think that is what is a bit odd. It's not always common, right? It's rather surprising.
So they have this bit here to all 3 bits really to cover different versions of GNN. Yeah. That's how I saw it, right? So it might not be exactly what's common practice in ODEs, but the idea is that it's an ODE. It can be seen as a dynamic system, and it covers all the GCN versions.
Yeah.
That's how I saw it. So, and it's important because, for example, this graph stage model, which has also the residual connections, it's one of the best so far. I think we use that quite a lot also. It's covered by taking this theta, the omega component as 0. You can recover the normal GCN by setting omega and the W tilde 0. So you just have this standard part right in the middle. That's the original GCN. You can also recover other models like GCN2, or I haven't seen this one, by choosing omega 0 and making these 2 W's convex combinations. I would imagine in that paper they use this convex combination as a memory term, possibly, right? Because you want to preserve the original inputs, if it's any useful, or maybe to stop oversmoothing too much.
When they call it source, right? So that usually means that you apply some overall true potential. Now it just means that the source seems to be the starting position of your system.
Yeah.
Funny.
Yeah. Right. And then we consider a class of energies which represent those three terms. So if you look at here, these terms correspond to the terms in equation 5. Really. Okay. Now we do a bit of math. No need to go into details. But the point is that we end up with a formulation of the ODE. So there's the gradient of the energy. Right. This is not the direct energy anymore. It's like energy they define. We end up with the ODE for this energy term, where matrices omega and W appear only as symmetric matrices. This will make our math much easier later, because later results have assumptions that these two matrices are symmetric. Obviously, it also makes computations more efficient. You don't have to, you have to store only half the matrix. Operations are more efficient and so on. So this is an important bit, because we have omega plus omega transpose making the matrix symmetric. Okay, so we write the final version as equation 9 with symmetric matrices here. Okay, any comments here? I guess I can just add that the direct energy is also quadratic. So is the energy we found here. So it's a generalized version of the direct energy.
I found it interesting why they didn't solve the matrix ODE directly, and instead they sort of vectorized the feature matrix, because sort of there are lots of methods to solve sort of matrix ODEs, but yeah, I don't know. I was just.
Does it matter?
I guess not, but it would make the rest of the computations that they did later in the paper sort of obsolete with when they vectorized it. Yeah.
Sometimes you can solve them separately, these subsystems, so that could potentially be quite interesting to take special cases of that.
Yeah.
Oh, and also I'd be interested to see, like, because they restrict the weight matrices to be symmetric, like what would happen if you don't have that restriction?
Oh, the theorem doesn't work out later. So it's not really restriction. The argument is that. Now can you mute? Thanks. The office is very noisy today. So the argument is that these become symmetric automatically, right? So there is no real assumption, and then later the proofs depend on those symmetric assumptions. Next, does it answer the comment, the question I have?
So they never actually say that okay, we're gonna set this matrix to be symmetric a priori, or does this symmetric property come out of the split that they do?
So when we design a GNN, we enforce symmetricity there. Yes, when we create a GNN model, we assume that the weights are symmetric. But the argument is that we can't do that.
So 8 follows from 7, right? So if they're saying if I define an energy that has these properties, necessarily it is asymmetric. The flow has these symmetric components to it. I think that's all it is. And you could go the other way, probably the other way around. You probably can derive 7 from 8 just as well, right?
Right. Yeah. But there's the system. What I was thinking is when they design a new model, they're like, oh, there's a GCN, let's make it better, right? In that model, they make those weights symmetric. And that they are arguing that assumption on the model is covered by this theory.
Yeah.
Okay. Let's talk about this attraction and repulsion parts. We had a quick look at that image earlier, right? And the point is that, again, we can do with some reformulations for the energy term. and we write this inner energy term with 3 components. Okay, let's look at all of those separately. So the dampening part, the left part, this measures the difference between the features, and I think this one is not as important in terms of studying the flow, but the traction and repulsion parts are, because this is how they argue that similar features, because we have the norms here, right? That similar features cause attraction in terms of making the features closer to each other on the next step, and repulsion if features are different. So let's look. Yeah.
My question, the first term essentially would be, if I were to cut the edges, this would be the solution based on the node features by itself, right?
Yeah, because there is nothing about the just symmetrics.
Yeah. Okay, thanks.
Yeah, good point. I should have said that. Yeah.
And this F0 would be in there. Is that
X0?
Yeah.
What's X0?
The initial configuration that
F0.
Yeah.
This is not time dependent though. So this is just for one instance in time.
Yeah.
So this is the update step, right?
Yeah.
True, but if the differential equation depends on F0, why would the energy itself not depend on it?
You would just have it. Oh, okay. I guess, yeah. I was just thinking you would just have a directly energy for F0. You have this form, but
Yeah.
yes, that's true.
Yeah, you think it must be in there, right? Because if it's really interpreted as a sink term or source term, then it probably should be, the source term should be also in there, and it probably is somehow absorbed. But the capital omega and W, they don't contain F0, right? F0 is sort of out.
I guess it doesn't have to, because it's the energy for the current state, right? That shouldn't be dependent on previous states.
So see what happens here. They said the theta 0 to 0, right?
Yeah.
This allows rewriting of W as a decomposing W into positive in terms of their positive and negative eigenvalues.
And so that makes sense, right? Because the source term was the only one that contains F0, and so that's where it falls out again.
Exactly. So theta 0 is here. The source term is, if you set it to 0, the F0 is gone.
Yeah. So essentially, it means your system does not depend on the original state anymore.
Not the energy.
Outside, yeah. Well, also the solution, right? If the assumption is that your system moves towards state with lower energy, and if that does not depend on the source term anymore, then the optimum energy must be only dependent on where we are right now and where we are right now compared to our neighbors, and how that evolves, right?
Can we see it as a regularization bit? Because if you ignore the original solution, you might have infinitely many solutions, and then you will need the source term.
Yeah, it just means that you should find a stable solution, right? Well, actually, that actually it becomes really interesting question because of this repulsion bit, right? If you have attraction, then you would sort of expect that. What are the FIs? If you had only attraction, right, you would expect over time your system equilibrates and everything is sort of the same thing, but that's not quite true because of the dampening term actually, which has this FI in there, which means that neighboring nodes could still have different solutions, right?
So in the simpler models, I think even in GCN, you would see that because the diffraction term would result in oversmoothing if you have too many steps, right?
Yeah.
Because there is no repulsion term in those models. That's why we get oversmoothing. Yeah, I think that's what you are saying, Alfred, is it?
But yeah, because this of course coming from physics, this actually is a really rich system where when you talk about like lattice system in general, where you have like magnets. Like magnets, when this is like you have these little arrows that are next to each other, and if they are attractive, you have a proper magnet that they all line up. What happens though if they are not attractive but rather repulsive? Becomes a lot more difficult, because you get sort of frozen systems where because the starting condition essentially can't move on because neighboring system sort of prohibited. And I think we would observe this here as well, where by tuning the topology of the system, one would probably get radically different solutions here.
What do you mean topology of the system? The just symmetrics?
Yes. For example, if
So
you,
they do that actually.
yeah,
It's actually interesting because they talk about that this is similar to switching the sign on the weights.
yeah,
On the adjusted matrix weights. For similar reasons.
yeah. So if on average you have 4 different neighbors or 5 different neighbors, I think you would get quite different things, right? Because 4 different neighbors, you can always do 2 that counteract the other 2, but with 5 that becomes impossible. Suddenly your system has many possible states of being of equal energy, maybe. I don't know. Sorry, I'm just babbling.
Well, there is a lot of stuff in here. That's true. They do cover a lot of theory, explaining many phenomena here. Just one.
Guess,
yeah.
Oh, so, yeah, go on.
Nice.
I'll speak later. It's fine.
Okay. I just wanted to continue really. So this omegas are positive definite and negative definite matrices, plus positive definite minus negative definite. That's important because the norm no, that's the decomposition, and then these signs in front of the norms will define which one becomes more important, right? And that leads us to low and high frequency enhancements. So they talk about this low frequency enhancement and high frequency enhancement, like LFE, HFE, and we show some bounds here in terms of how much the energy, the normalized energy, can change. Look here, I mean, it's positive. It's not negative, but it's also upper bounded by this spectral diameter. I think it's called spectral diameter.
Yeah. When you talk about frequency, do they mean spatial frequency, like the system becomes similarly smooth?
They mean the eigenvalues.
But the eigenvalues here are spatial in nature, right? They're
Yes.
not temporal, because you could think of systems where essentially it sort of oscillates back and forth depending on whether your neighbors, if you move in or out of sync with your neighbors, you could expect also those sort of frequencies there potentially.
So those are spatial because we look at this, like the equation 10 is only one time step, right?
Yeah.
It basically says in the current time step, how will this time step change the features?
Right.
For the
And
next one.
low frequency means we have smoothing, and high frequency means we have anti-smoothing.
Right. So that's the definition. Let's actually read it and unpack. Right. So if we have the GNN ODE initialized at F0, so we will call it as low frequency if the Dirichlet energy normalized by the value goes to 0, and high frequency if it tends to the upper bound. So that is upper bounded for T tending to infinity. Right. So this is actually important because we are saying that we have infinitely many time steps or layers, but they also mention in the future work that, well, in reality, you would have neither high frequency nor low frequency. You would have some mix, right? Because you don't have infinity. But that's fine. Right? For theory, it's good, and for practice, it's good enough. Okay.
That's what I was sort of wondering about, because well, in this system they have 2 stable fixed points, the LFD and the HFD states. But I mean, it's kind of hard for me to imagine the actual space that you're dealing with here, and if there would be any other fixed points in the system. Because I feel like the only way you can get other fixed points in this system is if you add sort of stochasticity to it, sort of have unstable solutions or like saddle point bifurcations. But yeah, I don't know what they meant by
that could happen though, right? If neighbors repulse each other, then you could potentially have situations where you have more than one stable fixed point.
Mm-hmm.
I guess, yeah, but yeah, that would just be like super interesting.
Yeah.
To think about.
Yeah, they mention it as future work because, well, you can't cover everything in one paper, right? Yeah, that's interesting. I agree. For now, we will look at low frequency and high frequency by saying whether the energy decreases to zero over time or increases to the upper bound over time. Okay, and this is correlated with the previous thing, right? We actually can show that. I think there is a theorem up here that says the continuous gradient flow in equation 9, this one up here, the original one, right? The generic one we defined earlier. This equation can learn to either, it can learn, right? So this is also important, can learn to be either low frequency or high frequency, high frequency enhanced, depending on the spectrum of W, right? So this is important because previously it was thought that that GCNs could this is important because some models, like some variations of GCNs, are never high frequency, and therefore they cannot recover. They cannot learn on graphs where we have heterophily. Okay, where we have differences between labels on neighboring nodes. So this actually explains limitations observed in experiments on a number of GCN variations. However, if we design the spectrum of W properly, accordingly, we can get models that can learn to be either LFD or HFD, which is what we do in the experiments. Any comments?
I guess I have a small comment. I thought this comparison with these other models was a bit unfair, actually, because the CGNN, the continuous GNN, and the PDE GCN, I actually did a paper on PDE GCN like months ago. They explicitly used only or like mostly diffusion models for their like GCN model. So I mean, those are always going to be LFD, but it's like they didn't try to claim that they were trying to like model heterophilic data. So I don't know. I thought that was a bit unfair, but yeah.
Yeah. So if the data is homophilic, then fine, right? Those models are is what you need. But they also show in experiments that even on such data, if you enable, if you design the spectrum of W accordingly, you can solve those problems just as well. Yeah. But yeah, I agree. It's not entirely fair, but fine. Cool. Next, from energy to evolution equations. So now we will actually define this. Now we will look at that. Do a bit more spectral analysis. So this formula we saw before, and we basically added encoder for the initial state to create the initial embeddings. And there is also the decoder that does the prediction. So this is a bit more practical about how exactly to create a GNN from inspiration from a dynamic system. I'm trying to find the important bits so we don't go too much over time. But basically, I guess the important part here is this theorem 4.1, where we can claim that if you have the number of layers, so it's no longer infinite time, right? Our models have infinite layers. If you consider the dynamical system here with tau time steps and only with the just symmetric speed, with symmetric W, right? And there's bound here on the negative, most negative eigenvalue of W holds, right? So these are lower bound and upper bound, both sides. If both these equations hold, then there exists a small delta such that for all nodes, we can actually compute the feature rho, the feature for that node. So the equation looks a bit convoluted, but I guess the other part is that, on the other hand, if the equation here is wrong, if 13 is the opposite direction, right? This is the reverse direction of 13, then we have a different formula, which is kind of similar, replacing a few terms here. And then we also have this big O delta. They are saying, look at the appendix for the exact value of the term, but it's basically a term bounded by the delta to the power of m. M is the number of layers. Okay. So this part gets a bit mathematical, but this tells us how we can, well, what we get if we design the GNN is being inspired by our findings before. Really, that's the main message.
So what was the DI again?
Let's see. What is DI?
In equation 15, the square root.
That's the degree.
Yeah.
Because over smoothing, you converge to
Yeah.
basically a vector of just the square root of the degree for each node. So
yes, I see.
I found this last section the most difficult one. But I mean, at least you should be able to get the main point here, right? If you want to go into all the details, might be a bit difficult. But yeah, the DI is the degree. Yeah. Okay. The corollary is important here, which says if the equation 14 holds, right? If we build a if we have the features defined like here, then the system is HFT for almost everywhere, F0 and FM, well, diverge, no, converging to F infinity. Subject to, I don't know what this infinity means. What's F infinity? Does anyone read this part? What's
that's
F
at T equals infinity. That's the
all right, so the
stationary point.
Yeah.
Yes.
Right. Okay, cool. That makes sense. Yeah. So this is the convergence to the stationary point. Thanks. So basically, this tells us that we can define the high frequency or the low frequency models using equation 14 or 15, right? And in each case, the stationary point for F's is also given. Right? In the low frequency case, it's 0. Higher frequency case, it's well, it's delta time. It's given with the delta.
Yeah, it's essentially the eigenvalue of that thing, right? This eigenvalue filtering. Yeah.
Cool. Okay. Here they talk that in general, neither highest nor lowest frequency Laplacian eigenvectors constitute ideal classifiers, because there is always finite depth to our models. We spoke about this before. Cool. Oh, they also mentioned about the residual connection. I briefly mentioned this, but the residual bit is important, because otherwise, basically, if G is not bipartite is another interesting case for graphs, because it creates a very large divergence in the eigenvalues, right? So if G is not bipartite, and we remove the residual connection, so we end up with a simple case here. Like this is the like the GCN, except there is no linearity either. With W symmetric, then dynamics is LFD always. Okay, so this is important because this basically tells us that whatever we do, because there are some models that try to fix this this problem, if we are missing the residual bit, then we will end up with an LFD model, okay, which can only work if you have a homophilic setting. Cool. Guess this bits we can scroll down. Just a quick note, more general terms. Here, this is important because they also study a setting where we don't really have an energy anymore, but we can, because if you have the nonlinearity, this is no longer the energy as defined in physical systems. However, they could show that this new system evolves similarly to one defined by energy. Okay, and they basically have the same inductive bias, which inductive bias means that there is the same sort of control between LFD and the HFD cases. Okay, and this theorem here shows that the C plus denotes the most positive eigenvalue of this matrix. Again, the matrix depends on the graph structure and the weights. Okay. And then you can see that these two systems, the energy one bounds the new one we just defined from below. Okay,
these equations don't tell you anything about the dynamics, right? It doesn't tell. It only tells you what your final state is, but it doesn't tell you how long it would take you to get there, right?
Well, so this basically says as the F starts converging, the energy one also starts converging, right?
Yeah. But of course, that is because it's really interesting. Conceptually, right? In these graph neural networks, you think when you start somewhere, you take one step. The most you know is about your very nearest neighbors, and in the second next step, you know a little bit about the neighbor afterwards, and so on and so forth. Of course, if you take these time steps to be smaller and smaller and smaller, but then make the interaction also weaker and weaker and weaker, you sort of could say naively that you touch on all the other states in your network, which is probably not true either, right? So it would be interesting whether one can, from the dynamics, sort of infer an effective radius of nodes that each node sees before it has converged to a final state. And that would sort of give an idea of what is the effective neighborhood of a node that truly matters for the problem. And I would think that probably very much also then depends on the topology itself, how interconnected things are. So it could be very, very interesting question.
Well, see, it depends on the topology, right?
Yeah. But of course, this equation just tells you it does converge in some bound. not necessarily how fast that is. Yeah.
Yeah, exactly. So this is but this is actually also common way of showing a relationship between convergence, right? This is used also in like optimization methods. It's
Yeah.
not. It's sometimes you just don't know the speed.
Yeah.
Yeah.
Cool. Would that be Vahan? Was that the point made by Alvi, which was on resolution and how it can affect the reaching this the final steady state? Would the because we have the smoothing operation between the fields, would the smooth transition from one node to the other be more important than the resolution at of the the entire what is it, the adjacency matrix that decides the topology?
Yeah, the topology is given by the Johnson matrix, right? But I didn't really understand the question. It was about your comment. Maybe did you get it? Oh, yeah.
I think
It was talking about the resolution. That would there be a way to decide the resolution? But I was thinking, would the
what's the resolution? Sorry, the resolution of what?
oh, the time step, was it?
The tau. That's what you mean. Tau.
No. I think
the time to convergence.
no. Is it? You were trying to say that. No, actually, I've forgotten myself. It was something to do with between two nodes. The resolution would be. Actually, Avi, could you remind me? I've forgotten myself.
What I was saying, that the time to convergence gives you a sort of time limit, right? And if you could sort of get the integral of what each node sees in that time from any other node, you would see that some nodes have only a very weak interaction with another one, and even if the time for this weak interaction is long, the integral might still be small. But you probably could give these interaction integrals and give every node in the system a weight of how much that node ever affected any particular node in the time it takes for the thing to converge. After it converges, the interaction drops off to zero anyways. And so I would think that gives you a sort of neighborhood of effective nodes, a node sees. It is interesting how that relates to the spectrum of these operators. And I don't know for sure, but I don't think there's a strict relationship between the spectrum of an operator and the dynamics of how fast it goes. Typically, one would say that the difference between the second and the largest, second largest and the largest eigenvalue tell you something about the system, right? I forgot what it was. Probably Naya knows better.
Yeah, something to do with the magnitude of the eigenvalues. Like the larger the eigenvalues, the faster you converge.
But it still doesn't tell you how quickly it does. But however, there are systems where it does. I think there are systems, there are some properties that make it true where the difference in eigenvalues also tells you something how quickly it is for you to converge. And if you of course could estimate this, you probably could estimate how long it would take for your system to stabilize. But there's probably some very serious, very complicated math behind this. I just don't know it.
There are 30 more pages to follow and maybe find out about the math. Well, not today. Okay, let's quickly look at a few experiments. This graph on the right is interesting because this is basically an artificial synthetic experiment where they control the homophily in the data and measure on test accuracy. The graph is the model presented here. There will be also graph NL, which is the model with the nonlinearities. And they basically argue here that even with very low homophily, these models start quite high. But like MLP is finally straight line, right? Doesn't matter homophily because doesn't study relationships between nodes, right? You basically assume there is no just symmetrics. And the other ones increase in performance with homophily, which makes sense, right? All these models, GCNs and NEG prod and whatever this prod, those are assuming homophily in their features. It's just a small experiment to show that. Okay, and the last table, this one is a real life experiment using all kinds of methods, a few famous ones, GAT, GCN, GraphSage, and many others. Some of them I don't actually know, but our models are the Graph and GraphNL, where they basically design the weight symmetry properties accordingly for the problem setting. And there are a number of benchmark data sets. You know, the citation one, there Cora is also citation. Film, I don't know what's film. Is it film reviews maybe? I don't know. Squirrel, but those are basically big graph data sets. Some of them are actually, I think, especially this Texas and Wisconsin, I think those are models that have high heterophyly, and some results showing that, well, these models are not always the best, but they do well across all data sets, right? That's the main point here. Often best, but even if it's not best, it's actually very consistent. Yep. We spoke about future work before briefly, but any final comments, questions?
Vahan, I have one question on the bit that I think that I didn't understand is how they enforce the. So when they update the weights, how do they make sure that the matrices always remain symmetric? Is it part of the loss function, or is it just enforced extrinsically?
I think you can basically update one part and then make the other part repeat itself, right? I didn't see any specific details how you do that, but
wouldn't you be able to control this via the weight update rules, that once you start with a symmetric weight matrix and your weight update rules are also symmetrized, you probably always stay symmetric? I think probably something like that.
Yeah, I actually didn't see how exactly, but I don't think it's a big problem, is it? You should be able to preserve symmetricity.
True. It's just pure for the sake of computational expense, right? Nothing functional about it.
What do
you
you
could
mean?
probably do some sort of like Cholesky decomposition, where you just get one side of the matrix and then do a product, and you always have a symmetric one. There's probably loads of different methods.
Also, if anything, that makes the method even more efficient. They actually mentioned somewhere here that compared to GCN, it's more efficient because matrices take less memory, because they take half the memory, which makes computations more efficient. They actually mentioned it somewhere in the experiments, I think.
Cool.
Yeah. Anything else?
Oh yeah, cheers.
I thought it was interesting how they never actually looked at the dynamics of the features themselves.
Yeah.
They don't look at the dynamics of the system, they just look at the energy.
Yeah.
And I don't know if that's enough. I don't know if that really tells you enough about the evolution of the system, or like how much information that tells you. Because you just look at the energy, right? You don't look at the actual dynamics of F or the actual ODE. So
yeah,
I don't know, it's a bit weird, I think.
Yep, that's interesting.
but I think if you know that your energy doesn't change, and they show that this is then proportional to to your system being stable, that sort of says something, right?
Yeah, I guess, yeah.
Cool. Thanks a lot. I'll stop recording, but we can continue conversation.